All right. Now that we've explored, various different types of mathematical tools we could use to manipulate our thermodynamic functions, let's go back to the beginning and let's look at that equation we had for that expanding gas test that we wanted to use. Okay? So we had delta S is equal to ds dt plus ds dp dp. And we saw from our Maxwell relation that we could rewrite ds dp in terms of volume, the change in volume, and changing temperature with respect to or at constant pressure. Okay? That's what we got for the Maxwell relation. But for ds dt here, though, we haven't really, our relationships didn't really give us anything that could be useful. We can't really translate. We didn't really find anything in which we could translate a measurable property into ds dt. Okay, and so here to get ds dt, though, what we're going to look at is something that we've already seen previously, that you have seen since MEB1. And so to get this, what we're going to do is we're going to revisit the fundamental equation for internal energy. Okay? And so du is equal to, in terms of its partial derivative, it's this. Right? dV constant S dV. Right? And then what I'm going to do now is I'm going to take the derivative of everything with respect to dt. So on the left-hand side, du dt, that's going to be equal to du ds v ds dt. Oh, and this is going to be a constant volume. Okay. So we have ds dt constant volume plus du dv constant s dv dt constant volume. Okay? Alright, so essentially we just divided everything by dt at constant v. Alright, quick things to point out here. We have a dv dt at constant v, so that's just 0. So that knocks out this whole second term. Here, du ds constant v, we know from earlier that this is just temperature. Okay? And so what we have here is du dt constant v is equal to temperature, and then that ds dt of volume, at constant volume, right? And so we're closer now, right? We were looking for this. Now we have an equation with that in it, where temperature is something that we can measure. But what about this? du dt at constant v. Well, we know that from the definition of the constant volume heat capacity, that Cv is just equal to du dt at constant v. Right? And so what this tells us is that ds dt at constant v is just going to be equal to the heat capacity at constant volume divided by temperature. And this heat capacity, this is something that can be measured in experiment. Using a calorimeter. Okay? And so what this tells us is that our delta S for that expanding gas, we can now rewrite it like this. Minus constant P dP. Okay? Alright, and so we see that just from invoking, various different relationships, mathematical relationships among our fundamental equations, we now can relate measurable properties to something at the molecular scale. Okay? Alright, and so this heat capacity, it's fairly useful derivative, has a name. And in thermodynamics, there are also a couple of other useful, what we call named derivatives. The more proper name for them is a second order coefficient. Okay? Alright, and so some other ones that you've seen before, constant pressure heat capacity, that's just the partial derivative of enthalpy with respect to temperature, constant P. Using our various mathematical relationships, we could show that this is just equal to T times the partial derivative of entropy with respect to temperature at constant P. So that's one we've seen before. Some other ones that you may not have seen before are things known as, one thing is known as the coefficient of thermal expansion. You'll see this abbreviated as alpha. And this is going to be equal to 1 over volume of dV dt at constant P. Alright, and so physically what the coefficient of thermal expansion would be like if you heated something, how much does its volume change by? Right? So if you've ever dealt with any sort of metal working, you know that when you heat a metal like to a really high, by a really large amount, so your delta T is very large, you'll see that your metal sort of expands. Okay, so that's we quantify that by measuring like the coefficient of thermal expansion. All right, another sort of related named derivative is what we call the isothermal compressibility. This is usually abbreviated as kappa T. And this one is minus 1 over V dV dP at constant T, hence the isothermal name. And so this is one where you'd be looking at how volume of your system changes when you increase pressure. Okay? Right, and so, I wanted to present these because I wanted to compare them to a common assumption that we've made in a lot of the problems we've dealt with so far when we encounter liquids or solids. So a lot of times we just immediately assume that the solids or liquids are incompressible. And so by making that assumption, what we're saying is that alpha and kappa are equal to 0. Okay? But in real life, or under sort of real processes, we don't really, the incompressible assumption is like making the assumption of an ideal gas or something, right? So whenever we're dealing with real solids and liquids, alpha kappa T would not be equal to 0.